Okay, so let's get started. Let me just do a brief introduction. This is a PR mini course. I want to emphasize that this mini course is sponsored jointly by our economic theory initiative, for which Naveen is the director, and also by PER, for which Yanku is the director. So today's speaker is Rajiv Vohra. Rajiv Vohra is the Ford Foundation professor at Brown University, and he is a leading figure in economic theory. He has made fundamental contributions to general equilibrium theory and coalitional game theory. Today his talk is going to be on far-sighted stability. Okay? He has made some recent breakthroughs in this area, so we want to learn what he's going to tell us about it. So Rajiv is also an Econometric Society fellow. Besides his academic work, he has also served as the Dean of Faculty at Brown University and Department Chair for many years. So now, let me give you Rajiv Vohra, the speaker.
Thank you, Ching. Thank you. My plan today is to actually go back to some work that Debraj, Ray, and I did many years ago, because I think in some sense all of our interest in the idea of farsightedness in coalitions goes back to some very well studied applications in economics. And they all have to do with externalities and the difficulty of trying to understand how coalitions might behave in equilibrium in a world with externalities. So I'm going to make a very conscious attempt not to talk about stable sets, core, so on and so forth, for reasons that will soon become clear, because I think when you think about a world with interactions across agents where externalities are present, there are lots of issues to worry about when it comes to coalition formation. Okay, so let me start by basically giving you a very simple overview of what kinds of problems arise when you think of cooperation or coalitions in a world with externality. So I'll try not to go straight into the models and into the mechanics of things, but just to give you a very quick sense of what the old literature in coalitional games was about, and reasons why it may not be well suited to deal with some contexts in economics. So I'll begin with a paper of ours from 1997 that has to do with, well, let me get straight into it. I mean, these are just the papers that are going to be involved. So let me set the stage. So think of a situation where we are all a bunch of people sitting in this room. We have to make some decision about what actions we are going to take. And suppose for our purposes, suppose it's possible for us to make a binding agreement. So this is not the world of non-cooperative Nash equilibria and so on. At least in principle it's not, because we are able to write a binding agreement. That's the premise. And a lot of people, when they hear that, will probably say, well, in that case we know what's going to happen is the outcome will be efficient and so on and so forth. But let's go slowly through this kind of argument to see whether that's true or not. So we are not worried about enforcement. So this is not about mechanism design. It's not as if we know exactly what to do and we are setting up things to make the outcome self-enforcing. Binding agreements are possible. Once they are written, they'll be enforced. But the question is, what in equilibrium will be the nature of the agreements that are signed? What will people, when they are able to make joint agreements, what will they agree to? And the negotiations that lead up to the signing of an agreement may very well turn out to be non-cooperative. At some level, it's going to become very difficult, or perhaps not that productive, to talk about what is cooperative and what is non-cooperative. In fact, one of the themes I think that will emerge from this is maybe we shouldn't talk in those terms, because the that knife edge kind of distinction may not be so productive. Okay. The second feature of this story would be that you may have different groups of people doing their own joint agreements. So there may be, one group of people who sit down and make one agreement about how they will behave, and the remaining people may have their own agreement about how they will behave. And the interaction across the coalitions will then be non-cooperative. So by coalition, we basically mean a group of people who have agreed jointly about what to do, and they'll be playing competitively or non-cooperatively with other coalitions. Okay? And as I said, one of the important questions for us is, what will be the equilibria? Will they turn out to be efficient? Why, if they are or not efficient, why does that happen? So first of all, our dissatisfaction with the classical cooperative theory comes from the following observation. If there are no externalities, many voting applications are like that. Many, the exchange economy is one of those very important models where you can describe for any coalition, for any group of people, what their opportunities are if they were to be on their own without worrying about what's happening to the group outside this coalition. Right? So if there are no externalities, what you can do is write down the utility possibility set for every coalition. Right? And that serves as a basis for, aggregating within each coalition what the possibilities are. And then that gives us what's known as a coalitional game or a characteristic function game. Basically what it says is that, the model is described like this. There's a set of agents, and there is, for every coalition S, there is a set of utility possibilities that they have. That's the description. And then the question is, what kind of outcome should we refer to as stable or an equilibrium outcome and so on. Okay? So when there are externalities though, that's not your original model, right? It's a case in which people have actions, strategies, and payoffs depend on all of the actions. And when I take one coalition aside and ask them, what is it that your opportunities are? What is your utility possibility set? There isn't such a thing, right? So the original game is, let's say, defined in terms of a normal form. It's a completely different model. In that model, if I were to take a group of agents, call them coalition S, of course we know what their strategies are, but do we know what their possibilities are in terms of utilities? We'd have to know what other people are playing as their strategies to figure out what the utilities are. But there was a way in which people would take something like a normal form game and convert it into a coalitional game where you describe the payoffs for each of the coalitions. And the way in which that was done will turn out to be important, but the idea was to reduce a game in strategic form to a characteristic function. And then you're back to the familiar world of once you have a characteristic function and you know what your equilibrium concepts are here, you start from this, convert it into this, and then apply your favorite equilibrium concepts such as the core, the bargaining set, the stable set, the nucleolus, whatever you want, right? And so that was one way of dealing with cooperative equilibrium outcomes starting from an environment that had externalities. Yeah.
We can ask questions, right?
Of course.
So, one could just write down like a utility possibility set for a given coalition as a function of, the sort of sub-partition
of what's left behind.
of what's left behind, right? Is that a...
Often that's possible, but you see that that requires more information than is here, right? So that may be, in fact, many times it's possible to extend this model, and it's not so unreasonable to go from here into what's called a partition function, okay? And I will talk about that. But yeah.
I have another question. So this also related to step 1, right? So after we done with step 1,
Yeah.
Which is kind of an exogenous process, and then we apply the solution concept on the outcome of step 1. But one could think of another possibility where the step 1, the conversion itself should be part of the equilibrium, should be part of the solution concept, right? So why we need to separate the two steps, but then only apply solution concept on the second step?
I am not arguing for this as a good thing to do. This is just my view of how things were done. I'm just telling you what used to happen in this branch of the literature. That if you were interested in these kinds of solution concepts, and someone said my primitive model of the economic model involves some normal form game, can you tell me what cooperative solution concept I can use for this? The standard practice was to first convert it into some characteristic function, and then say, okay, we can tell you what happens here, right? And the problem is precisely in that very first step, the conversion of a normal form game into a characteristic function. Because all of the conversions I am aware of are in some sense ad hoc. They will assume something or the other that is a bit of a problem, which I will point out as I go on, right? So there is the alpha characteristic function, which was used to define the alpha core. There's the beta characteristic function, and so on. Take this as an example. The alpha core is a concept defined for a normal form game. But really what it is a particular way of converting the normal form into a characteristic function, and then applying the usual core to that characteristic function. That's what it is. So how do you, if you're interested in that, how do you do this? How do you do this? Well, you say for every coalition you give me, any S, what I'll do is I'll ask the following question. What would be their payoff profiles feasible for them in the worst possible case regarding what people outside that coalition choose to do? Okay? So you assume the very worst. You say that my coalition can only get what it is guaranteed to get regardless of what outsiders do. This is ad hoc in the sense that the motivation of the outsiders is not to minimize your payoff. It is to do whatever presumably is in their own self-interest, right? So that's the sense in which it is ad hoc. It's an assumption that's made about what you believe will be the actions taken by people outside your coalition. And this is how you define for every coalition their set of feasible allocations. And so as you can see, it's going to make it particularly difficult for coalitions to imagine doing something better than what's proposed, because they are always imagining the very worst. We won't leave this room unless we absolutely guaranteed that regardless of what crazy things other people might do, we are going to be better off. Okay? Yeah, so I will actually define this later on along the way, but that's the basic idea. That's roughly what this is about. Okay. So let me, so the problem here, I would say, is that these coalitions that are determining their utility payoff sets, V of S, are not predicting how the other people will behave. They are assuming the worst. I mean, that's a certain kind of prediction, but it's hardly a rational, thought through prediction. Let's take an example. Okay, what is this prediction problem? Let me take a familiar example, a 3-person Cournot model. Suppose it's symmetric, suppose you have linear demand curves and so on. And now our problem of what agreement will be formed among these 3 firms is like this. The 3 of them are sitting around the room. They could agree to a cartel that sets the monopoly output and divides that, let's say, equally among the 3 of them. That's the best possible thing they could get. They have the ability to do that. Should they do that or not? Well, again, just to be clear, I'm not worried about the enforcement problem. I'm saying that if they agree to this, they can carry it out. It won't be a problem. There's no antitrust law that will prevent them from doing it, let's say. Yeah, so we are not concerned with this. We are assuming that away. What is the question that we are concerned with now? Will the three-firm cartel form? Will they decide to form the monopoly, the monopoly firm and share profits equally or not? It seems like they should. Why would they not do that? But let's go slowly through what the options are. Because now, in this three-firm situation, there are three kinds of things that can happen. Either all three of them agree to an agreement, or they all walk away and then it's like non-cooperative play. Nobody's cooperating with anyone else. But there's an intermediate thing too, right? That two of them write a joint agreement and one of them walks away. And then I'm going to assume that there'll be non-cooperative play across those two coalitions, one consisting of two firms and one consisting of a single firm, right? And yeah, so if there are all going to be singletons, let's take the Nash, Cournot Nash to be our metaphor for what happens in that. That's how I want to think of non-cooperative play across all three of them. There are these two situations that they all three cooperate, nobody cooperates with anyone, or there's the intermediate case. And our problem at first glance is just to see, is there some obvious way of figuring out what is going to happen in equilibrium? Let's not assume Nash. Let's not assume efficiency. Let's try to figure out what would happen given the fact that binding agreements are feasible. They're feasible. Will they arise in equilibrium or not? So here I've taken a simple example where in the grand coalition, they can get a total profit of 36. If they divide it equally, they all get 12 each. The Nash equilibrium gives them all a profit of 9 each. And when you look at this intermediate coalition structure, the one guy who's outside, it's like a duopoly where the two inside the duopoly have to share that duopoly profit. So if you start with the three of them in the room and one of them says, let me imagine what would happen if I leave. Let me not assume the worst. Let me not assume the most optimistic thing. Let me try and figure out what would happen. If I left and the other two were to stay together, that seems like a great outcome, right? It's better than staying with the monopoly, with the cartel, right? So one would be better off if the other two were to remain together. Now, is that a good or a bad assumption to make? Well, we should ask whether that is to be expected or not. Is that what we should predict? Given the numbers we see here, that's not a good prediction because, once they are left together in the room, they're not going to write an agreement to form a duopoly in the industry. They'll also walk away because 9 is what they can get in the Nash equilibrium, right? So this is the reason why the cartel should stay. It's an equilibrium for them to form the three-person coalition, because there's no incentive for any group to leave as they do that. The threat is that you will end up in a Nash equilibrium. Not because that's the only thing that's possible, but that is the prediction that makes sense. So I haven't described the normal form game here and so on because I just want to give you a very quick sense of what the issues are. There are externalities here. My profit depends on what other people are producing. And for any two of us to figure out what our opportunities are, we need to know what the third person will do. Notice, by the way, that if you are doing the alpha core calculation and you asked an individual firm, well, what will you get if you're on your own? The answer will be 0. Why? Because the worst is that the other two will drive the price to 0 and you'll end up getting 0. So you should be satisfied with any non-negative amount. That would be the prediction from the alpha core. Next example.
Sorry,
Yeah.
but I guess maybe this will become clear later, but implicit, it sounds like, I mean, what about the question of, so if we consider the coalition of 1 and 2, 3,
Yeah.
then implicitly you're saying that, the 2, 3 won't write the binding agreement because by not writing it, they expect 999.
Yeah.
But that sort of presumes that the fact that they haven't written the binding agreement will become, it's observable, or, 1 will realize that 2 and 3 haven't written the agreement, or will
Well,
learn that they haven't written the agreement?
Well, what I'm saying is simply that 1 will predict that they won't.
But I mean, if they expected 1 to play whatever quantity level it is that corresponds to the profit of 16,
Yeah.
then they would rather collude and get 8-8, right? Is that right? I can't accommodate.
Yeah, so the again, I haven't given you the full normal form, but it so happens that if there's one firm alone and the other two have formed a duopoly, in this example, it will turn out that the two groups will get 16 each.
Right.
So within the duopoly, they'll be sharing that, and each one of them will get 8. That's how it works out.
But that's, I mean, if they expected 1 to actually produce the quantity corresponding to 16,
Yeah.
what
That's
is
that's the Nash equilibrium of two firms.
But that's better for firms 2 and 3 than separately choosing quantities that are best corresponding to one's 16 quantity, right?
Yes.
So I guess all I'm saying is that it's,
Why do they? So
if they expect, 1 has walked away and
Yeah.
1 conjectures that we're actually going to do the duopoly,
yeah,
then 1 is going to choose.
we'll end up with 16.
And
But
then, so I guess it seems relevant whether they form the duopoly or not becomes observable to firm.
does it? Well, I don't think so. Let's suppose it becomes observable.
Yeah, then I see the logic.
Then you see a lot. But suppose it's not observable. Is it not reasonable for the first firm to predict that after I leave, they are going to indeed break up and play non-cooperatively with me?
I mean, there may be multiple Nash
Maybe.
equilibria, right?
Yeah, but again, admittedly, I haven't worked out the whole thing here because I just want to start with a motivating example. Suppose these are the only numbers that matter for now.
But there is a literature on the stability of cartels, right?
Yes,
Internal and
yes.
external, so that's linked to this. And if I remember well, they were saying for small numbers it can be stable to have a full cartel. If you have more players, it breaks down.
Yeah. I think we will see some of those ideas crop up. I think what's important in this is just a 3-person example. I think what's important here is that when a coalition gets formed, it should have a prediction about what's happening to the rest of the people. And not having that prediction and relying on some assumption about how they will deal is totally unsatisfactory, which is what the alpha core and the beta core and all are doing. So we don't want to do that. And so the question is, how do we make the prediction? Let me give you one more example before I go into the models, okay? This is a public good problem. This is a bit cooked up. I'll later talk about one where you'll see everything explicitly, but it's cooked up to give you a very quick look at the kind of problem that can arise. This is a different from the previous one. Here, if the grand coalition forms, everybody makes a high contribution to the public good, they get a per capita payoff of 1. Let's suppose that if nobody cooperates, the Nash equilibrium is a payoff of 0, 0, 0, which is a bad outcome. Here, if one player leaves the 3-player group, as before, that's a good thing if you can sustain that outcome. And now what happens to the other two is that they still make some contributions. They won't make 0. They will, the amount by which their contribution goes down is such that they end up with 0.25 each. And now it seems like the the right prediction to make is that they will not disintegrate into the Nash situation. Okay? So here I would say that it would be bad to leave the grand coalition only if you predict the Nash outcome, but there's no reason to predict that. If the other players were trying to mini-max you out, yeah, that's what the alpha core would say, no, stay there, because if you leave, the terrible things will happen and you'll all end up losing. But there's no reason to fear that in this example. Okay? So these are just two motivating examples which point out what the difficulties are when you want to think about coalitional notions of equilibrium when there are externalities.
You were stating it in terms of cooperative versus non-cooperative, alpha core, etc. But some of it, and this may be related to Navin's question, seems to have to do with farsightedness versus myopia.
Yes,
Like
yes,
myopic.
yes. I think, in fact, if I have emphasized it too much, I don't want to emphasize that much the idea of cooperative versus non-cooperative.
No, you said you don't want us to think like that.
Yeah, my only the only thing I will say is that we are starting with the presumption of feasibility of cooperation, and then whether it emerges or not, it remains to be seen. And this is an example where we wouldn't expect it to emerge, in the sense that this intermediate coalition structure is what is likely to arise. It's a symmetric game, but that's what's likely to arise. What's not going to arise is the horrible, complete free riding where everybody's getting zero.
So how does that, raises the public good example? So one is on his own, he gets the public good, but he has to, how does he get two? That seems high if you're on your own.
Yeah, it's a cooked up example. So I will give you a less cooked up example later on.
Right.
But the idea is just that, imagine 3 levels of contribution, low, medium, or high. And in the efficient outcome, we are all contributing very high.
Yes.
In the complete free riding, we are all contributing very low. And in this intermediate stage, it can happen, depending on the parameters, that when I'm alone, I contribute low, and the other 2 contribute a medium amount.
Okay, so they cannot exclude me from the public good.
Exactly. It's a pure public good, right? Yeah. So I'll get to a better model of the public goods, but this is just to say, look, this could happen. It might happen. Something like this may happen. Now I think it might be useful, as we were talking the other day, to bring in coalition-proof Nash equilibrium, which is something that people have seen. It is related to some of the ideas that we are interested in. On the other hand, it's very, very different. So the story is useful. Let me start with the story that Bernheim, Peleg, and Winston give for coalition-proof Nash equilibrium. This sounds like an equilibrium concept where coalitions can actually do things, but it's really about coalitional communication, about coordination, not about binding agreements. Coalitions are allowed to talk, to communicate, to coordinate, but in the end, they are only going to be allowed to choose strategies that are self-enforcing. They cannot actually write a binding agreement and get it enforced. So here is the story they tell. All players meet in a room. There's free discussion about what to do. Anyone could leave at any time. Any group could leave at any time, right? And they have their strategy choice already made. But the problem that arises when you think about leaving the room is that now you have to think about what the remaining people might do after you leave. Plus, there is the farsightedness issue of, well, they also have to worry about what would happen if some subset of them were to leave, and so on and so forth. Okay? And they are looking for an agreement, but again, this is a self-enforcing agreement. Not a binding agreement, a self-enforcing agreement which will be immune to this kind of problem where by communicating things people might depart from that original agreement. It is a refinement of a Nash equilibrium. So this is all done in the static case with the normal form game, and there's a solution concept that is defined based on this story. I have to caution you that the definition is the definition and the story is, I mean, once you look at the story and you look at the definition, you might be tempted to say, yeah, but that wasn't clear in the story, or, is that really the case? Maybe the story needs to be changed a little bit. But if you really want to be very, very precise with the story, you might as well just go to the definition, okay? And the definition proceeds by recursion. You say, look, if n minus 1 people have left, then what is the remaining person to do? Well, that remaining person, it's like a reduced game where there's a one person left in that game, and they choose the best thing they can given the actions of those who have gone, right? And now look at the two-person case. To be self-enforcing, we are only going to be interested in looking at pairs of strategies for these two people that are Nash equilibria in this reduced game. But they can communicate, and if there's one Nash equilibrium that Pareto dominates the other, they can coordinate on that better one, right? When you get to the third, when you get to 3 players, you have to now be a little more careful, because what they don't want to do is simply take all the Nash equilibria and see the ones which are Pareto efficient within the class of Nash equilibria. That's kind of very simplistic, because it doesn't take account of this possibility of what might happen when you go beyond the first step. So they do it recursively. In the 3-player case, you say, what are all of the Pareto efficient Nash equilibria of each of the 2-player games, and ask whether some 1 or 2-person coalition could do better by going to one of them, because that's what they predict would happen. Okay?
So I forgot, do they allow randomization here?
No. Actually, I think they do, because the definition is not done with the randomization, but I think their example where there isn't a coalition-proof Nash equilibrium is even allowing for a randomization.
But here, it's a refinement of Nash equilibrium.
Yeah.
So at least the joint controlled lottery are not allowed here.
Sorry?
The joint controlled lottery, where the randomization are correlated.
No, I don't think those are not allowed.
In the sense, the communication within a coalition is still limited in some sense.
Yes, I think so. Hmm? But anyway, the point of my putting up this slide is to just try and draw the distinction between this and what I am about to do now. This is about non-binding agreements. They're not really agreements, they're self-enforcing strategies. It's about coordination, it's about communication. And it's a refinement of Nash equilibrium. When I allow for binding agreements, I'm allowing for things that are not necessarily going to be Nash. Okay? So, change the story. So think about the same story, and again, I might find that the story will not do justice to the definition, or the definition may not do justice to the story, but again, in a simple way to get to the definition, suppose everyone is there in one room and negotiations begin. Some joint course of action can be enforced if it is agreed upon. Any coalition is free to leave the room, but now I am going to allow, there are many rooms in this building. Any coalition could leave and walk into a different room. In the end, we may have lots of coalitions in lots of different rooms. Lots of people in different rooms, those are just all the different coalitions. And I want to stick to the simple idea that across these rooms, the play is non-cooperative. They are not any longer in a position to make a joint agreement. So conditional on a partition of the players into the different rooms, that's a coalition structure, that's a partition of the players. Each coalition plays non-cooperatively with other coalitions. We'll formalize that. This part is not going to be difficult. And each coalition that forms has to worry about further fragmentation, just as in coalition-proof Nash equilibrium. So some of the elements of the story are similar, but I'm giving more prominence to the idea that different coalitions may form, and in fact they may be playing across each other. The coalition structure may be important, And of course, the biggest difference is that in principle, it's possible for any one of them to write a binding agreement if they wish to. So strategies are self-enforcing across the coalitions, but not inside the coalitions.
Like internal stability versus external stability. I'm going back to that, sorry.
What is this?
Internal stability is you have a group of 3 firms, let's say, that cooperate, and it's not going to break up. And then external stability is they won't agree to take on a 4th player. So in a way, you're saying once people have been put in a room, you don't let them attract another. You don't let them renegotiate with other coalitions.
I'm not sure it'll be exactly that, but many of these ideas will be present in what we do.
Yeah.
So we may.
The ability of a cartel, that's what these people have in mind.
Yes, but I think in that literature the emphasis is very much on that one cartel.
Oh yes, I'm not saying this is a very special case and a special way of approaching it.
But it's an important case. So I do want to come back to the Cournot cartel example. But for now, this is a story we are trying to formalize and looking for a solution concept that captures this story. Okay, so that's the question. What is the solution concept? So let me try and define that now. So now I'm going to the formal model to try and capture this last story on the last slide. So we take a game in normal form. There are externalities, of course, everywhere, and a coalition structure is just a partition of n, and pi is the collection of all coalition structures. R of pi will be all the refinements of pi. That is, if pi prime is a refinement of pi, that means that every coalition in pi prime is a subset of some coalition in pi. There are no mergers. There are only further refinements. So fix a coalition structure. So the first thing I'm going to do is, well, what do we mean by competition across coalitions? That, as I said, conceptually should not be very hard to do. We just say that a strategy profile satisfies the best response property given the coalition structure if for every coalition in this coalition structure, it's not possible to make a coalitional deviation that will be a Pareto improvement. So it's not possible for any coalition in this structure to find a YS for itself, which will Pareto dominate for them the X. If S is a singleton, this is just best response for an individual player, right? And denote by beta of pi the set of all such strategy profiles. If there turns out to be a unique one, that will make life very easy for us, right? Otherwise, we'll just have to carry around the possibility that even conditional on the coalition structure, there might be different things that could summarize the competitive actions across these coalitions. But I should point out here that in case this, for every pi, this beta of pi is, suppose this thing is unique, then of course I could describe for every coalition given I could describe this, right? It would be just the payoff they get in a beta, if the beta is unique. Okay, this is slightly more general than the characteristic function. This is a partition function. And sometimes it'll be useful. It'll be useful to reduce the model to something like that. Okay, so that part is I think straightforward. This is describing the set of self-enforcing strategies across these coalitions. For instance, if the coalition structure is pi star, by pi star I mean the finest coalition structure, everybody's on their own, there's no cooperation in this coalition structure, then beta of pi is the set of Nash equilibrium. So I'm taking self-enforcing to mean Nash, just to fix our ideas and move on. If pi is n, then beta of pi is any Pareto optimal, any Pareto efficient thing, I shouldn't say X, should be anything Pareto efficient for this set of players. Okay, it's not X, it's a set of Pareto efficient strategy profiles.
Somehow it seems that pi being partition is quite important here.
Yes.
Think about
Yes.
prisoner's dilemma. If I allow both individual collision and ground collision, I will get non-existence, no?
No. So once I tell you what the partition is, then you can figure out beta of pi. If I tell you that they are not cooperating, then it's the usual prisoner in the prisoner's dilemma. They play their, the Nash equilibrium outcome. Okay. If they are together, then you ask that if they could write a binding agreement, what would they do? They wouldn't play the Nash. They would play the Pareto efficient.
They have binding agreement. They do not need to enforce it.
They don't need to enforce exactly. So this would be the Pareto efficient strategy profiles. This is wrong. It should be Pareto efficient. So those are the two extremes. In a two-person game, those are the only things. And so it's not surprising that in a two-person game, I'm going to get the very trivial and obvious conclusion that typically the possibility of being able to write binding agreements will guarantee efficiency, and you won't get a Nash equilibrium. Cooperation will be in efficiency, and non-cooperation will be in the usual thing. Okay? But we want to go beyond the two-person case. And to do that, we first begin by settling this. If you tell me what the coalition structure is, beta of pi tells us what happens, right? The more important question is what in equilibrium will be the coalition structure and what will be the equilibrium strategies. In a lot of these interesting models, what will happen is that Pareto efficiency is usually going to be synonymous with the grand coalition forming, because when you don't have that and there's a coalition structure that is different from the grand coalition, it typically will mean that the competition across the coalitions will, for the usual reasons, given the externalities, will produce inefficiencies. Okay? So the basic requirements for something to block a given strategy profile, so X is being proposed for the grand coalition, let's suppose, and the basic requirement for some other proposal to block it are the following. In the final coalition structure, Y must be satisfying this best response property. So I'm just saying that if some coalition from here decides to go into another room, they are making some prediction about what will happen after that and so on and so forth. And if they expect in the end what will happen is Y, that Y should have the property that conditional on that final coalition structure, it is Nash across the coalitions. That's one. Second, this Y, for it to be thought of as a final outcome, should itself be stable against this kind of deviation by some other coalition from inside that room. That's the farsightedness notion. Don't just look at what will happen when you leave, think through what will happen after that. And finally, imagine that the prediction that we are making when we block a given proposal by predicting Y and going into our room and imagining what other breakups will happen, that our prediction of this final coalition structure should have the following property. That each of the coalitions, suppose there are many smaller coalitions that are expected to form in the end. It should be the case that they would be worse off if they didn't break into those smaller coalitions. So it would be in their interest to go along with this proposal. Or that if you were to merge some of them, you'd get instability. The simplest case to imagine, I mean, there is quite a bit hidden in this. The simplest kind of blocking would be a coalition leaves the room, that new coalition structure turns out to be stable, beta of pi is what is going to be played there, and you see whether you can gain there or not. But also, by the way, check whether you are subject to further internal deviations.
So I think the same question I'm asking it again. So with
Yep.
point 2, again, I'm still having trouble sort of trying to understand exactly what we're envisioning, because, so we're in a room,
Yeah.
and now sort of Alessandra and you are contemplating leaving.
Yeah.
And, your point 2 says we should also think about whether Alessandra will then want to leave you.
Yes.
Right?
Yes.
But, if that depends on what the rest of us are doing.
Yeah.
If we are going to be acting, assuming that you guys are in a coalition, maybe you will actually want to stay in just the two of you. But,
Yes.
If you think that if you then split up, we will actually react to the fact that you have split up.
Yeah.
You may want to break up. And so I'm still having trouble sort of understanding whether we should be thinking of this as sort of eventually whatever sub-coalitions form and so on, everything becomes observable.
Yeah, I think that is probably best. Otherwise, it may be harder to justify the idea that conditional on the coalition structure, what's being played is Nash-like strategies.
Okay.
Otherwise, I would get into questions about how to define that non-cooperative equilibrium, and I don't want to go beyond Nash as my metaphor for what happens when there is non-cooperative play.
I mean, an alternative would be to just say that, look, when you guys leave, we play Nash of the coalition that's left versus the structure that stayed.
Yes, yes.
But you're requiring more.
I'm saying that would be maybe the first level prediction. Okay, so conditional on our leaving and staying together, let's look at the Nash between the two of us and the rest of the society.
But your point 2 is not, your point 2 is requiring more, right?
It's requiring more. So it is starting by saying, look, first let us settle what these Nash-like things are conditional on the coalition structure. If we agree that the coalition structure is two people together and n minus two people together, we compute this beta of this coalition structure. And that is what we believe will happen if that coalition structure is imposed or happens to be the final coalition structure. That's all. If it's going to change, then we should ask, well, what will happen in that changed coalition structure?
So can I just tell a story, just
Yeah.
to understand. So there is the whole team there, we're all playing together. Then some people start creating an A team because it's better for them. If the the other people don't react, then there's the possibility that this new team, called the A team, is
Yeah.
going to fracture. At the same time, there are people in the B team, in the team that's left, that might become attractive to people who are already in a separate team. So you're looking at all these possibilities.
No, I'm doing something simpler. Something simpler where I'm saying in the first instance, let us agree on what are the accepted outcomes if the coalition structure is fixed in stone. That's easier to agree on, right? For example, if it is everybody's in their own coalition, it's Nash.
So
If everybody.
still with the pie, yeah. We are
Yeah.
keeping pie.
Yeah, because I think so that's the first part of the whole exercise. First is, given conditional on pi, what is the meaning of people playing Nash-like across these coalitions? All right? Once that is known, it's like you sort of know this. If these guys are unique, you sort of know this. You know what will happen if I tell you what the coalition structure is. But there is still a question that you will want to answer when you're thinking about leaving the grand coalition and forming your own coalition. And that is, after we do that, are there further incentives for people to change that coalition structure? And if there are, then we'd be looking at the beta of that pi prime or whatever it is. Okay? So think about these different coalition structures. What you predict will be the coalition structure, and once you know that, this best response thing is what will happen in that eventuality. So the idea that when a coalition forms, it should ask itself, will there be any incentives for subgroups to leave that coalition? becomes actually important with externalities. Otherwise, that's not such a big, it's not a huge problem otherwise. But here it is. Such as, in the Cournot example, the very first one, the two people who are left behind were not going to stay there. It didn't make sense for them to be together. It'd be better to play Nash. All right? So that's all that is. That's this idea of farsightedness or consistency, that when you make a move in your own interest, the very same forces that led you to break away from the grad coalition may cause people inside your group to leave you, the rest of you. So think through all of that.
But somehow I didn't see, just when you look at this subcoalition and you want to look at the internal stability and consistency of that.
Yeah.
But there could be which I think did not capture, but you can tell me whether it's correct or not, that some member of this subcoalition actually form a new coalition with some members of complement coalition. That's not captured here, right?
That's not captured here. Very good. That's very good, Chingmin. I think that's going to be very important for this definition to be even written. And if you look back, exactly the same issue arises with coalition-proof Nash equilibrium. And so what we are doing, we are guilty of exactly the same kind of thing.
Okay, so
because
there, if you have this, you cannot do the kind of induction definition. But
and we will also be doing an induction, and we won't be able to do it if we don't have that. Okay? So that again is going to be similar to coalition-proof Nash. What's different is, the main thing that's different is the possibility of a binding agreement. That plays a bigger role here is that there are all these other possibilities for coalition formation. It's not just one coalition versus the rest. So I'm going to give you the definition now. And you tell me whether it conforms to the story or not. I will not be surprised if there are gaps between the story and the definition. So, bold-faced B of pi will be the set of binding agreements for some coalition structure. So once you give me a coalition structure, I'm now going to define what I mean by the set of equilibrium binding agreements. Our final interest is actually going to be in B of n. That if I think of n as the original starting point, which is where I expect to see first best efficiency, what are the binding agreements given that coalition structure? Will it stay or will it break? So start the recursion by, of course, going to the obvious place. Go to pi star. What are the equilibrium binding agreements if your coalition structure is that finest coalition structure? It is just a set of Nash equilibria. Okay. Now we can start, right? Now we can get going. So recursively, suppose that B of pi prime has been defined for all refinements of pi. It's been defined for all refinements of pi, so it hasn't been defined for coalition structures where there are mergers going on. Okay. Once people leave this room and go into another room, the only thing that can happen after that is that some subset from there might go into a new room, some subset from here might go into a separate room, but it won't be any going back to people who were with you in the past. That's an assumption, just as in coalition-proof Nash, for reasons that are the same. The reasons have to do with this recursion. Otherwise, we are going to be stuck. So start with that, and suppose we've defined B of pi prime for all refinements of pi, and take some candidate best response strategy profile in this coalition structure pi. Has to be one of these if it's going to be an equilibrium. We'll say that this is blocked by some pi prime x prime from a refinement if there is some coalition that is interested in going to that pi prime. Call them the set of perpetrators who actually initiate this breakup of pi into pi prime. Because remember, pi prime may not just be a one-shot departure from pi. It may involve many, many breakups. So there may be one coalition that breaks up, predicting that others will break up in a certain way. But the important thing is that there is one of these coalitions which is responsible for triggering this change. And that is the set of perpetrators who make this change. X prime is a binding agreement in that finer coalition structure pi prime. There is some leading perpetrator for whom this is better, right? So this conforms to the usual idea of blocking, that if there is a coalition that blocks a given proposal, it must be because eventually they're going to gain, but here the emphasis is on eventually. And eventually also means that this outcome at pi prime is truly an equilibrium binding agreement, that there won't be any further change from there. Because recursively, we've already defined these guys. Okay? So there is that credibility and consistency built into this. And then what we are saying is that for the other coalitions that may be involved, this won't happen in a 3-person game, but if you have a larger game, there may be a prediction of a whole cascade of things happening for good reason. But good reason must mean that if you were to recombine any of those guys, that will not be good for them, or that won't have an equilibrium. So this would be a way of constructing what we call an equilibrium binding agreement for pi, by first constructing these things for every refinement of pi. Then you come back to this pi, and if B of pi leads to no change, then you know that there is a best response equilibrium such that it doesn't change. And our interest is usually going to be, what is B of n? Is it going to get blocked or is it not going to get blocked?
So can I say that you're looking for deviations that are robust? The only deviations that are allowed are those that are robust to further deviation.
Yes.
So a deviation that is not robust to further deviation, I don't have to worry about.
No, it's not that you don't have to worry about. You then follow it through.
I follow it.
And see where it is going to go. So every time you start with a potential deviation, some coalition makes a move. What this is saying is, ask that after they make the move, is that a stable outcome?
Right.
If it is, then just check whether it's good for them or not. If it is not, then don't give up yet. Then keep going. Where will that go? And ask, is that going to be good for the coalition that was trying to make the move? If it is, then that's fine.
All right. So if it is fine.
Yes. So I will define a deviation.
That's that.
Yeah. So a deviation must be a binding agreement wherever it is expected to leave, expected to settle into, and there must be some leading perpetrator of this whole chain of events who finds it advantageous to go there.
Is it possible at all to flatten this recursive definition by saying something like, for every pi, we have eventually to just decide on xi of pi for everyone.
Yes.
We want each excess index S subscript S for a coalition. Excess of pi must be efficient for S within pi.
Sometimes it's
looks like your beta of pi. And we want there to be no profitable move to a pi prime that improves the utility of everyone. No, that doesn't work. No, it cannot be everyone.
can't be every-
That's too much.
Yeah, but sometimes it is possible to simplify this. Yes.
You said, just kind of stuck on your words from you said that the final outcome has to be advantageous to everyone who moves.
No. Only to there is some leading perpetrator identified as one of the coalitions involved in actively moving. Because what can happen is that some group can move off, and what's left behind is not actively done anything. Right. So they may not be better off. It's just other people have left them in the situation they're in. So
But then at the end of everyone's moves, the perpetrator would be better off.
the perpetrator would be better off.
So you're not requiring that they be better off each step.
No.
So can they bluff?
Sorry?
Can they essentially bluff, like branching off, flooding the market in order to induce other firms to retract quantity?
Well, no, because the only reason they're not allowed to bluff is because at every step they're playing beta of whatever the pi is. So if you and I leave the room, everybody believes, and in fact that is what we are assuming is going to happen, is that we'll play whatever the beta is, if that were to be the final outcome.
Okay, so they do have to optimize each step.
They do have to?
Optimize.
Yes, yes, yes. But again, I think the emphasis is on what the final stable outcome is going to be. We are not thinking about payoffs instantaneously. The only thing that matters is where things will settle. Okay?
So here in the sense that it's a single deviation. I look at one deviation and then I just want to test
Yes,
that deviation.
yes, yes.
Yeah.
So it's it's sort of like we may start from n, some S1 goes off, you have n minus s, and you might have from here S2 and S3.
Yeah.
That could happen. And these guys will go here, expecting to go here because they predict that these two will in fact split up like this. So S2 and S3 may not be better off compared to there. They're only better off by doing this because this is not good for them. They've been sort of put in a position where from that point on they're willing to make a move because it's in their interest. Okay? So I think I've already mentioned this before. If you have a two-player game and there is a strategy profile that Pareto dominates every Nash equilibrium, then obviously there will be an equilibrium binding agreement in which you see the grand coalition, the two of them form together, and you won't see inefficiency. Right? Because the alternative is really bad. There's no reason for anyone to walk away from the efficient outcome. But when there are more players, things are not that clear cut. We actually already saw that in the two examples, even though they were not fully spelled out. But that's the kind of thing that could happen in a three-player game. And if the alternative to an efficient agreement is not Nash, but some kind of partial cooperation in some intermediate coalition structure, then there may not be this first best efficient outcome. But note that that will happen only because, or only if, we don't predict going all the way to the bad Nash equilibrium outcome. Okay? I won't talk about this because I did say in the beginning of the talk I'm not going to mention these words today, so I'm not going to mention them. But if you want to go through that exercise, it may actually simplify some of these things to suggest that there is a dominance relation which can make all of this fit together very, very nicely, and I won't then have to go through some of the gymnastics I've had to. But I think that I don't want to do that because this is a sort of, a primitive way of going from the what I've just done here is the way to naturally, I think, build the equilibrium definition. So let me not talk about that, at least not today. So here is, Bernard, this is an answer to the question you asked an hour ago, I guess. So what is this public good say? And so we thought it was very important for us to at least have a proper public goods model in which we could ask whether this is just an entirely cooked up problem or not. So here I have 3 agents. Imagine a public goods problem, although you could just look at the numbers, but that won't give you any feel for what's happening. So each agent has 3 strategies: low contribution, medium contribution, and high contribution. Okay? And there is one dominant strategy equilibrium, which is that everybody takes a free ride and they get that. The symmetric thing that Pareto dominates is that everybody makes a high contribution. Right? but there's all this other stuff in between. What's going on? What's going on there? So because each player has this dominant strategy, which is A, it's fairly easy to see what would happen if any one of these guys would leave. Okay? So let me ask what would happen. Okay, just hang on a second. So that's the Nash outcome. That is our Lindahl equilibrium. That's Pareto efficient. This thing is not. Suppose we are trying to sustain this. Is it possible that this will actually be the agreement that these three people write when they are capable of writing a binding agreement and enforcing it? Suppose player 3 says, well, you know, what if I leave the room? I am off on my own and we are in this world. Okay? Now, the other two in principle are able to coordinate. They can go anywhere in this matrix. Where do we expect them to go? We don't expect them to go there if they can coordinate. 1 and 2 would go here. They won't make a zero contribution. They'll make a medium level of effort. There's no reason for them to contribute the efficient amount. Okay? And note that doing that is better than the Nash outcome. So they can coordinate, and if they knew that this was the world they were in and they could write a binding agreement, I expect them to do that. Which leaves the perpetrator of this, player 3, at 3.7. Okay? If we had gone to a Nash equilibrium, this would have been a terrible thing. It would have been a bad thing for player 3 to precipitate. From the grand coalition, going to the Nash equilibrium is not a good thing, but if you can take a free ride, make a small contribution, and anticipate that these guys will do this. They don't have to. You don't have to anticipate that they'll produce the maximum amount, just the medium amount, and you're better off. And that is an efficient outcome in this table for players 1 and 2.
Is it possible to construct an example like this with perfectly transferable utility?
Yes.
It's possible.
Yes. So I think all of those questions come up whenever I give you a very simple example.
Well, here it doesn't work.
Well, this example actually comes from a TU example.
But here, player 2 and 3, for instance, they would always coordinate on the high contribution equilibrium if they're on their own, right? If you add their pairs, let's say, not really well.
They would. So 1 and 2 would prefer this to this.
2 and 3. 2 and 3, sorry, and then 2 and 3.
So 2 and 3, well, it's entirely symmetric, so I think you should be able to see it in the first table itself.
Yeah, so I guess the issue is right. So I guess the question, I guess what Bernard has in mind is, even though 3 is left, you can still sort of transfer money to him, or he can transfer money to you.
After 3 has left,
No, yeah.
3 has gone away.
No, just at some point in your argument you said, sorry, I think I got the numbers mixed up, but you said these two, one of them left, there's 2 left together, and they're going to agree to make a median contribution.
1 and 2. 1 and 2. So 1 and 2 are making decisions in this table, right? And 1 and 2 will decide to go for B. They'll both make a B contribution, not A and not C.
Okay, that's right. So my objection doesn't work.
Yeah. So this is So there is even a fully worked out model that will do this. The point of this is just to emphasize that this is a robust example. There are all strict inequalities everywhere, and I can even write down a full-blown model where this would happen in this case. Okay. So there's a robust example of inefficiency. Now, this is a way of, I don't know why I'm defining all these things, but in some cases, as I said a little earlier, in some cases, things are not as complicated as that definition. Thank God. Sometimes you don't have to worry about all of those various ways in which things can change. So let me take symmetric game, and TU meaning that there are transfers permitted. This might help. So a symmetric game is just one in which everyone has the same kind of strategy set, the same payoff functions. If let's not worry about these definitions. Just means symmetric and transferable utility. The assumption that will be useful is, we call this monotonic. What it says is the following: that every coalition enjoys positive externality from the merger of other coalitions. This will be true in the Cournot model, right? That if I'm one of the firms in this sort of world with different coalitions, different groups of firms, I will end up with a higher profit in beta of pi if there was more concentration outside my firm. I mean, those guys may not like it, but I would like it because more concentration while I am still the same size is better. Suppose that's true, this will be satisfied in that example, for example. If you take a symmetric TU game that is monotonic, then here is a trick that will make things very easy for us. Take for each coalition, assume that they will divide their total payoff equally. Remember, it is a symmetric game, so this may not sound so strange to do. So in principle, I have lots of different things that could happen. There are transfers possible, but in each case, let's do a simple-minded thing and look at the equal division of the worth of every coalition, and define the equilibrium binding agreements for this simpler model. It turns out that the equilibrium coalition structures of this equal division assumed game are the same as the equilibrium structures of the original game with full transfers. And this is often helpful in computing these things. So in the previous game, for instance, it was enough to just look at symmetric things going on within each coalition. If you don't have monotonicity, if you don't gain from mergers, this may not be true, and then it really will be more complicated. So if you want to look at the symmetric Cournot oligopoly, now we are saying it's one of the things that will make life easy is you can just assume equal division within each coalition in the symmetric Cournot oligopoly. I mean, if n is equal to or less than 5, what I've written here is what I mean. If you have 2 or 3 or 4 firms, the equilibrium binding agreements will give you efficiency. They will form one cartel. They'll be all together and they'll earn the monopoly profits. If there are 5 of them, then that's not going to happen in equilibrium. The equilibrium binding agreements will not involve one grand agreement among all of these players and full efficiency. But the equilibrium is not going to be terrible, because that, I think, is a more general insight in these kinds of models, that if you don't have full efficiency, it's because things are not going to be as bad as Nash. Okay, I'm not going to go into further details of the results in this model, but this is just meant to give you a sense of what you can do with normal form games without trying to convert them into characteristic functions. The one important assumption is the one that allows us to do the recursion. So you could ask, well, what if it's really truly free-flowing communication, not just communication, but agreements can be written again and again, what will that lead to? This model will not get there. Just as if you ask that question in a coalition proof Nash equilibrium context, there again, it is precisely because of this restriction to internal blocking that you can do the recursive definition. Otherwise, the definition wouldn't get off the ground.
But is there a paper that deal with that issue where you can?
Where you can, and it involves words that I'm not supposed to use today. Yes.
So if it's possible to go back to the example we had.
Yes.
Yeah. So if 3 goes to top, so low contribution, and if you allow A and B to randomize,
Yes.
in their binding agreement, couldn't they agree to play 8, so they randomize between A and B, actually forcing 3 to have a table of 2 top? So in that sense, wouldn't it be possible for randomization to be better?
How does that help them?
Because it would put the payoff at 3.2 of player 3, and then maybe eliminate that route.
No, but they don't gain. 1 and 2 don't gain.
No, it's the same, right? You have the same payoff, I guess.
Yes,
Same
and
expected payoff.
and we are assuming what is the usual assumption, that you don't move unless you are better off. If I were to have a cooked up example, I could avoid that too, but this is not a cooked up example. That's why it is turning out to be the case that their aggregate payoff is the same.
Exactly.
Right? Yeah. So, but they don't have a reason to move from this.
Except if the reason will be to have player 3 think that that he doesn't want to go there because it's going to lower the payoff.
Yeah. So let's say that in this example, allow only pure strategies or work with the conventional definitions which say that, you know, if there is an indifference, it doesn't mean that you will break the indifference in one way or another, that I'll allow for something to be in equilibrium if you can't do better. Okay? So, Jingmin, I think I mentioned a paper by Diamond, 2D, and Shui. That is an answer to that question, to say, look, this equilibrium binding agreements is restricted in terms of internal blocking. How would we handle the more general case if I wanted a more general definition? And that will have to be, I don't know, have to be, but I think it's likely that it will not be a recursive definition, and that's what they do. Okay. And now I'm going to switch gears. So let me give you a very quick introduction to the next part. This has all been, you know, the blocking approach, take a normal form game and try to figure out from first principles what it is that the blocking by coalitions will yield in terms of equilibrium. Another approach to all of this is to say, look, this is all going to get us tangled up in these questions of, you know, internal blocking, doing this kind of recursion. Instead of that, suppose this is the case, that then I have a well-defined partition function. I could even begin from this, and I think that would not be unreasonable. Many problems of externalities can be seen that way. I can describe a coalition's payoffs once you tell me what the rest of the coalition structure is. So there's some literature that will deal with hedonic games, where there is a unique payoff profile for every coalition once you tell us how everyone else is organized. There are others where there may be transfers within the coalition, so those will be like TU partition functions. Okay? Let's begin with that, not with the characteristic function. I don't think I need this notation now because we've already been talking about characteristic functions. We haven't done anything with it. Again, I think I can skip this because, again, we won't be doing the alpha characteristic function. Suppose transfers are possible within every coalition, so I have a TU partition function. It's not necessary for many other things I'm going to say, but it'll make it easier to describe the model. So a partition function assigns to every coalition S in a coalition structure a worth V of S comma pi. That's what the transfers allow me to do. Each coalition's utility possibilities can be described by a number given the rest of the coalition structure. And now, it's fairly reasonable to imagine that we take this alternative approach, which by now is very well developed, of coalitional bargaining. So it's going beyond, for example, think about Rubinstein-Stahl, where you have a two-person bargaining problem, alternating offers or some variation of that. You're given some protocol, and you are trying to figure out in equilibrium what will happen. That is, if you think about it, a model with binding agreements. We are just once we agree on something, there is no problem enforcing it, right? What if there are 3 or more players? You could ask the same question. Now you could have coalitions form. The first player who moves, suppose there are 10 people to begin with, the first person who's given an opportunity to make a proposal could propose to 3 people and leave, and so on. So even in the characteristic function, this is a well-defined problem and a pretty interesting problem. There are some papers on that, including Chatterjee, Datta, Ray, and Sengupta, I think in Restart some time ago. But what we are about to do next is coalitional bargaining in a partition function game. This is one of our papers, again, from a long time ago. This is in Games and Economic Behavior, 99, where I think the title is Endogenous Coalition Structures or something like that. But again, it's motivated by the idea that there are externalities. And in a world with externalities, the characteristic function will not do. And now if you think about coalitions forming through a process of bargaining, coalitional bargaining, the equilibrium there is another way of getting at what the equilibrium coalition structure would be. This is very closely related to a paper of Francis Bloch on problems like this. What he was studying was, well, the leading example there is also Cournot model. He assumes that within each coalition things will be divided equally. And then one of the assumptions that will be important for us, he also had to use the same sort of assumption. Okay? So those are the 2 papers that are closely related to what I'm about to do now, right? So this is another way in which equilibrium binding agreements might arise, not in that other way, but through a very explicit non-cooperative kind of model, really. So again, I don't know, is cooperative, non-cooperative? I mean, we shouldn't care too much about that. Coalitions are forming, and there is a process by which this happens. Given the proposer at the moment, that person decides who to make offers to. If they agree, that's the end of them. But notice now that when the proposer makes a proposal to a coalition, and suppose it is less than the grand coalition, the proposer and all the responders have to predict what will happen after they leave the game, because their payoff is going to depend on the final coalition structure. So it becomes a more difficult problem of predicting what will happen if we were to accept the current proposal and leave the game. We have to predict what the final coalition structure would be. On the other hand, the method by which we'll make that prediction is straightforward, right? We will just look at the equilibrium of this game to predict where things will end up. Assuming we can.
I understand the role of version of exploring various forms of the game, the protocol.
Yeah.
At the same time, here it's not allowed to depend on pi, for instance. So there's a bit of an asymmetry because you're saying there's externalities in that V of S can depend on pi, but you're saying at any point in the game when there is a coalition S, the proposal order is going to be the same independently of the structure.
I think we could make it depend on what has happened thus far. So,
well, we can't make, yeah.
Okay.
Right.
So this protocol tells us when, some people have left the game, who is the next proposer. We could make it depend on precisely what the coalitions are that have left, but we can't make it depend on what the final coalition structure would be because that's not yet determined.
No, but then it can depend on what are the other coalitions.
It could depend on what has happened in the past. I think it could depend on the history.
Yeah.
It could depend on the history. Yeah. I'll have to be careful, but I don't think that the main issues will change. I don't think. So
But just, in contract theory, it's super important.
Who the proposer? How do we? Who the?
Determine
Yeah.
who is going to make a move and who's going to
Right.
the renegotiation process.
Yes. Yes. So I'm going to proceed with the assumption that this will be okay. I think it is. Okay. And then there's an order in which the people who have been proposed to either accept or reject. And so now that's our bargaining game where this is a partition function. Okay. What is a proposal now? A proposal is not just, well, we are going to divide $1 in the following way. It has to be a more complicated object. It has to be contingent on what our final worth will be, which depends on the final coalition structure. So it has to be conditional on the final coalition structure. So a proposal, if I am the proposal, I make a proposal to all of you, I have to say, look, guys, the proposal I'm making is this division if the final coalition structure is pi 1. This division if it is pi 2. This division if it is pi 3, and so on and so forth. All of that has to be part of the proposal. And when people accept, that's what they're accepting. What they get to consume in the end will depend on the actual outcome of what the coalition structure is. Yeah, I don't think the notation is terribly important here. It's just a description of what I said in words. That's what a proposal is. It is y of pi prime for all pi prime that are consistent with us forming this coalition and all possible conceivable subpartitions in the remainder, adding up to our worth given that pi prime.
So the proposal is only to the remaining proposers?
To a subset of the people who remain. So the way this game proceeds is that in the beginning, when we start at n, the protocol might say, okay, Naveen, you're the proposer. You're free to propose to whoever you want. You make a proposal. You could make a proposal to the grand coalition. You could make a proposal to some subset. They may agree or not. If you make a proposal to a group that agrees to this very, this contingent proposal, then you guys leave and you're done. We never see you again. The next time you show up is to consume based on being told what the final coalition structure is. Okay, so that's how this game proceeds, and that's how the other, even in the characteristic functions, that's how people did this. Right. So proposals can be accepted or rejected by the respondents. One option is to assume that the first rejector becomes the next proposer, but of course there's only one kind of protocol. Let me proceed with this and simply say that some variations are possible, but it's not just completely anything will go for some of the results. So yeah, once there is an acceptance, these guys leave. Okay? Otherwise, we have the usual 1 unit of time passes and so on. A stationary strategy describes a proposal in which your proposal or your response is not going to be conditioned on the history. And it is well known that once you go beyond the two-person bargaining problem, if you don't restrict attention to stationary strategies in equilibrium, you could get all kinds of things. Okay? So if we want some sharpness, we have to do this. And so a stationary perfect equilibrium is a collection of stationary strategies for which there is no history at which a player benefits from her prescribed strategy. There is, first, to get it out of the way, there is an existence theorem to say that there is a stationary equilibrium in a model like this. And it doesn't involve a lot of mixing, perhaps in the choice of the coalition. So the next, the more interesting thing perhaps is, what do you get in equilibrium, right? Do you get efficiency? Do you get the grand coalition? If I look at the Cournot model or the public goods model, what kind of coalition structures will emerge in equilibrium? Simplify to symmetric partition functions, where the only thing that will matter are the sizes of the different coalitions. Okay? What are the different cartels? What are their different sizes? That's all that will be important in this world. The numerical coalition structure is all that will matter. And now I'm going to give you an algorithm. So maybe the best thing to do is to suspend disbelief for a second. Don't think about, well, I don't know. Maybe you'll be thinking about the story, but I want to just give you first a mechanical algorithm. And this mechanical algorithm is the following. Suppose I have some sort of collection of positive integers, call that bold-faced n, and the sum of all these integers is k of n. Let f be the family of all such vectors where the total number of these things is less than n. So begin with n. I know that's the number of players in our game, but given any collection of positive numbers adding up to a number less than n, that happens to be k of n, all such vectors, construct now a rule. So now I'll give you a rule for coming up with a positive number given any such family of positive numbers adding up to something less than n. And the rule is this. The first step in the rule is that if there's only one number left, I have no choice. T of n will be equal to 1. If I have numbers n1, n2, n3, and they're adding up exactly to n minus 1, then T of n1, n2, n3 is 1. So I have to choose some number that is between 1 and what is left, n minus k. Suppose this has been defined for all numbers adding up to m plus 1 up to n minus 1. Okay? We just, from step 1, we know what happens when n minus 1 numbers have been assigned and there's only one left. In that case, just define the continuation of the original vector n by n, tn, and then t of n dot tn in the obvious way. Okay, so suppose I have told you already that that if let's say n is 14, then p of this is of course 1. That's step 1 in the recursion, right? And if I have,
what is the interpretation of T here? It's corresponding to the original problem, or should I just regard it as an algorithm so far?
well, this will, yeah, that's why I don't know whether it's better to keep the story here, but it will turn out to be the size of the next coalition that forms. Suppose n1, n2, n3 are the sizes of the coalitions that I have left. what is the size of the next one that forms? Okay? And then once you're given that, what is the size of the next one that forms? That is kind of what this is. So if there's only one player left, the size of the next coalition to form is a coalition of size 1. If there are 2 players left, the size of the next coalition to form could be 1, it could be 2. Okay? So once I have started this recursion, I should be able to move on from.
But then what is n dot t of n? What is that?
I just mean the concatenation is what it's. Thank you. Yes, you're just describing the rest of the sequence. Okay. Now, the way in which we will construct this t of n, I mean that case was trivial, but otherwise, the largest number available. So m have left. I can choose a number between 1 and n minus 1. Let me choose a number that maximizes the average worth of the coalition that would form of size t. Predicting that the final coalition structure will be that. Because from this point on, we already know from the earlier step how to complete the sequence of integers adding up to n. Right? So again, if I want to start from the very beginning, when there are only 2 people left, you say, okay, what would be their average worth if they were to stay together? What would be their average worth if you were to form a 1-person coalition? And then predict that after that there will be a 1-person coalition.
This is sort of reasoning backwards,
Yeah.
saying
Yes.
at every step when we look forward,
Yes.
we share equally the work.
Yes. Now you might say, why are you doing this? But then I'll say, well, this is just an algorithm. Okay, it's just a well-defined algorithm based on knowing the partition function. You give me the partition function, and I can run this algorithm, and I'll come up with some sequence of numbers like that. I might have 1, 5, 7, whatever. Okay. And so in the end, what I'll call n star is starting from when you have n people left and you run this algorithm, what do you get? You get a sequence of positive numbers that will all add up to n, and they've been constructed in this way. But of course, we were not doing this because the algorithm is in itself very exciting, but it is something that can be computed. The reason we are doing it is let me first tell you the reason we are doing this. The reason we are doing this is this. And I think it will sound very plausible that for a high enough discount factor, what you'll find is that any equilibrium in which an acceptable proposal is made with positive probability at any stage is going to be one in which whenever you say that some collection of coalitions has left the game, the next thing that will happen is that the next coalition to form will be this given by that algorithm. That algorithm was only looking at the average worth. But modulo the delta, that will be pretty close to how the worth will be shared in that coalition. The proposer in equilibrium in this coalition will get a little bit more than the average modulo the delta, and the rest of the respondents will get the remainder.
Is the delta multiplied by the size of the next coalition minus 1?
So if you think about what happens in the 2-person alternating offers thing, the proposer gets the total worth divided by 1 plus delta, because T of n is 2.
That I know, but
Right.
I don't know how it is multiplied by T of n minus 1 in your formula. I'm sure it's
T of n is the size of the coalition I'm forming.
right. So if there's
right?
no, that's similar.
But it is okay. No, it is, but it should also seem familiar, I think, because if T is 2, then
That's not it.
and when T is 3,
number of periods, you have to wait until.
No, if T of n is 2, it makes sense.
Yeah. And if T of n is 3, then it also makes sense. It's 1 plus 2 times that. Okay. Anyway, the point is just that the proposer will get a little bit extra, modulo the delta. And in fact, I will not need to assume equal division. It will be a result in equilibrium. So I don't have to assume to begin with that you divide everything equally in your coalition. Just make whatever proposals you want to make. In the end, this is how things will turn out. But there is an assumption that will come next. No, there's no assumption here. So this theorem is just fine the way it is. But the difficulty with this theorem is any equilibrium in which an acceptable proposal is made will look like this. So it's not on the primitives. It says that if you find me an equilibrium where there are no delays, every proposal is at every stage one that gets accepted, then the equilibrium coalition structure will correspond to the algorithm. The algorithm will predict the equilibrium coalition structure. So the question that remains is, under what assumptions can you guarantee that acceptable proposals will be made in equilibrium? And that comes if so we'll have to make an assumption to rule out delays.
Just another thing. So the n star is unique generically, or
It's unique in the sense that these are just numerical coalition structures, because I was looking at a symmetric game. So if the algorithm ends up with 1, 2, 5, 7, it means that the sizes of these coalitions will be 1 and 2 and 5 and 7. Yeah, up to relay. But it is unique because maybe I skipped over that. It is unique because I'm defining Tn to be the largest integer that maximizes average worth. Why? Well,
no, I get
yeah.
that,
But why?
oh, the largest integer.
The largest. So that's what makes it unique. Okay. So there are. If there's an indifference, you break it in favor of the larger coalition. So if average worth is maximized in size 2 and in size 3, this algorithm says pick 3. And the intuition for that is that as a proposer, you get to skim off more deltas the more proposers you have who accept your proposal. So there's a very good reason for uniqueness here. It's not breaking the indifference in a particular way. This is the way to do it. You always pick the largest one if there is an indifference. Okay? So the algorithm gives you a unique coalition structure. It'll turn out to be the equilibrium coalition structure in every equilibrium that is a no delay equilibrium. Can there be delays? Yes. And this has to again do with the fact that there are more than 2 players, and the fact that there are externalities just makes it a little bit even easier to generate equilibria in which there are delays. I think we are running out of time, so I will probably, through the argument, delays are possible. So in this case, for example, the algorithm will give us the coalition structure 4 and 1. What will happen in this game is that the first coalition to form will be a 4-person coalition. The next one will be a singleton, of course. That's the equilibrium coalition structure in every equilibrium with no delay. There could even be delay in getting to that coalition structure. But more importantly, there's also an equilibrium with delay in which this is the coalition structure. So delays are possible in equilibrium, and if you have a no delay equilibrium, the algorithm I gave you is the only one to worry about. That is an equilibrium. How do we rule out delay? Well, here is a condition that we need. This is the condition that the average worth of the coalition that forms after this has left, according to the algorithm, is not less than the average worth of people who will get formed later on. So there is no, it seems plausible, right? I mean, this is how you would make sure that no group or no person, no proposer has a reason to cause a delay because he's trying to come later. The reason you get this thing with delay is that there are two guys who want 4 per head. They can't get it to begin with. If they form a 2-person coalition, what will happen? If they form a 2-person coalition, that is what will happen after them. So they can't get this if they go first. They can only get this if they are intransigent, they in equilibrium turn down everything that comes, and there will be an equilibrium where 3 people will go away, they will go right away, and then those 2 guys will get. Of course, they lose the delta because of waiting by delaying, but that's still worth it. They can't do that by just forming a 2-person coalition first. So this is an example in which the coalition that comes second actually gets a higher average worth. If we make this assumption about the partition function, then there will be a no delay equilibrium. Everything will happen right away, and it will follow the algorithm. If I strengthen this a little bit, I can get it to be a unique equilibrium coalition structure, the algorithm that we had. There'll be only that and nothing else. I think that so uniqueness can be had by strengthening this assumption of non-increasing average worth, that delaying doesn't increase your average worth in your coalition according to the algorithm. So take a partition function, run the algorithm, see what it is. You can check these A's. If they satisfy this assumption, you will have a no delay equilibrium. The algorithm will give you the equilibrium. A slightly stronger version of this, and it will be a unique equilibrium. What about other protocols? Well, some results will continue to go through, others may not. What seems to survive in most of them is that this algorithm is pretty robust. This will remain an equilibrium. So it is, I think it belongs to most of the modifications you might make to the protocol, but you may end up with other equilibria. That's harder to rule out. But in the rejector proposal, with the strengthening of this assumption, this turns out to be the unique one.
Rajiv, sir, so this was for, I was going to ask you just to make sure it was about symmetric games.
Yes.
Was it monotonic games? Or?
No. So take any symmetric partition function, check that that non-increasing average worth holds after you've computed the algorithm. If that holds, then this algorithm will give you the equilibrium coalition structure. Will the equilibrium coalition structure turn out to be what is efficient? No. I think a big question here is, what about non-symmetric games? And it's not that it's impossible, but it's not easy, that's for sure. So we have a more general version of the algorithm in the paper, and there's more in Devraj's book on what to do in the non-symmetric case. I think more needs to be done there, in the sense that we were very, I think, irrationally obsessed with getting a result for the general case that would include the symmetric case as a special case. But that's a little, I mean, that you don't have to do. You could have a result on the symmetric thing and another one which excludes the symmetric thing, which is where I think one will have to go to deal with the, I mean, you can make some assumption that of genericity that will rule out some of the troubling indifferences, and you could do a general algorithm.
Why is that irrational? Why is that irrational?
Because we didn't succeed in doing that, and so ex post, it would have been better to give up on that desire and just try and get a result for the non-symmetric case. We are done with the symmetric.
It's just an expectational error. There's no
Irrational, yeah, it's certainly ex post irrationality. So what happens in the Cournot oligopoly here? Suppose I take a standard Cournot oligopoly with a linear demand function, and normalize some things. And if you give me the numerical coalition structure, this is the the payoff to any coalition is just the number of coalitions 1 over the number of coalitions plus 1 squared. It satisfies that stronger version of non-increasing average worth. And so according to the result, there's a unique equilibrium in this game. It'll involve no delay, and it'll be what the algorithm tells you it is. And according to the algorithm, there is a unique equilibrium coalition structure. It is not the grand cartel. It consists of, so now it's not just what is the size of the biggest firm, but what is the equilibrium coalition structure. There will be a number of singleton firms and a single cartel of size n minus L. And this L is a number, is the smallest non-negative integer that satisfies this. Now that you won't find, for example, if n is equal to 3, right? So you have to go beyond 4 or 5 before you will get a coalition structure that is not the grand coalition.
So that's there is this paper that I'm sure you know by Salem, Switzer.
Yes. 83, right?
Yeah.
And what they point out is that if several firms are already out there, then and the number of firms left is small enough, they will stick together.
You need a large cartel.
You need a large enough cartel that has to do with something like this.
So asymptotically is the whole economy. Because your L will be square root of n.
It is practically the whole economy, but there will be people who are lucky enough to be on their own.
Vanishing fraction.
A vanishing fraction will be on their own. But if I take a small number like 10 firms, then you'll see a fair amount of inefficiency in terms of the comparison with monopoly outcome. Okay. I think we better stop here for today because it's a good stopping point. The next thing I was going to do is a public goods example where hopefully it'll be more than just an example and we can say more about what will happen in equilibrium. Okay.
Is that formula intuitive to you?
I'm sorry?
Is that formula intuitive?
This inequality now, but the result is perceived as a paradox because you would like to have a theory of Cournot in which you can have oligopoly.
Right.
And here with a large number of things to choose with, you never get
A
oligopoly.
bunch of small.
Yeah.
Okay, so any questions? Thank you.
Thank you.
So this 1983 paper is a non-cooperative model or cooperative model?
It's the Cournot, it's just they look at you know it better than
Yeah. So it is not a full-blown equilibrium model in the sense that you start from scratch, but you could ask if I have a certain number of firms that are already out on their own, what is the threshold